Hello, in this video I'm going to take a first look at ideal gases, and this is probably the main topic within thermodynamics that we look at before we head off to university, and with good reason. I mean, if we're going to choose a phase of matter to model first, to try and describe in detail first, then gases are the obvious choice. We've seen previously when we've been discussing the energy, the thermal energy inside different substances, that when it comes to gases, I mean, the potential energy is negligible. We're only really concerned with the kinetic energy of the individual particles inside the gas. So this makes it a little bit easier to describe. That doesn't necessarily mean that it's going to be easy. I mean, the behavior of gas particles is still very complicated. So in an ideal gas, this is where we're making some assumptions. So we're making some assumptions. This is why they're called ideal gases. We're saying, under certain circumstances, this is how a gas will behave. Now, as to how accurately this will describe the actual behavior of actual gases, that is going to vary. And in some cases, it's a very good approximation. In other cases, less so. But that's what we mean when we're talking about an ideal gas. Let's try and set up some ideal perfect scenario that we can actually describe with precision. And this is something that you have to do in physics all over the place. I mean, not just in formal physics that you'd be doing at school or at university, and if you stayed on to become a physics professor or something like that. But, if you were going to be an engineer or some kind of data analyst, I mean, I've done some work looking at wind turbines in my day-to-day job. And in that, you're trying to make assumptions. If you want to say, how is a wind turbine going to perform? What equations can we use in order to describe the energy generation from a wind turbine? Well, you're having to make certain assumptions. No wind turbine is going to work perfectly when you stick it out there in the real world. You're going to have certain inefficiencies. But you can say, well, within these assumptions, we can say this is how a turbine will perform. So this is what we'd expect to recoup if we were going to build a wind farm in a particular part of the country. So you have to make these approximations. You just have to make sure your approximations and assumptions aren't too radical. They aren't taking you too far away from reality. And it turns out that with ideal gases, in a lot of cases, it's pretty close to reality. So what are these assumptions that we're going to make about gases then in order to describe them and do a more detailed analysis of their behavior? Right, we got a load of these. There's a lot of them we have to go through. So number one is that particles, we're going to treat the gas particles as indistinguishable point sources. So we'll say indistinguishable. So they're all the same as each other. We're not saying that any particular particle is different from any other one. And we'll say that they are point masses. So they've got no volume. This is going back to the days of, when we started off doing our kinetics and kinematics in classical mechanics. So we're saying they're indistinguishable point masses. So the point masses is also getting at the fact that there's no internal potential energy inside these particles. So there's no internal potential energy. We haven't got a structure to these gas particles where you might be getting, say you had 3 atoms in a row making a molecule which is part of this gas. There's no flexing here. There's no internal vibrations. We're ignoring anything going on inside the gas particle. So there's no internal potential energy or kinetic energy inside these particles. So that's one thing. We can also say that the size, because we're talking about point masses, that the size of the particles is negligible compared to the volume of the gas as a whole. So it's negligible compared to the volume of the gas. So again, we don't need to consider the size of the particles when we're dealing with the motion of them moving around. We're not saying if two particles were going to collide with each other, we don't have to think about the extent of the particles or anything like that, or if they're colliding with the walls of the container. Again, we're not considering the extent of the particle. These are just dots that are moving around. So we don't have to consider anything to do with that when we're analysing motion. Right, number 3, we're going to say there is a very large number of particles. Very large number of particles. And they are going to be moving in random directions at random speeds. So moving in random directions at random speeds. So again, we're just taking all kinds of sort of distinguishability out of this, moving in random directions at random speeds. Yeah, everything is as randomly distributed as possible. And this means that and I'll do a separate video on this, that we're going to be able to use an unbiased Maxwell-Boltzmann distribution. So this is a statistical way of describing the motion of the particles inside a gas. So we don't have to worry about that at the moment, but it's tapping into all this random stuff is tapping into the statistical mechanics that is sitting underneath all of this, and our distribution of energies, velocities of the particles in the gas. So yeah, we got that. We can also say that the particles are moving according to Newton's laws of motion. Move according to Newton's laws. So really we're saying with that they're not moving crazily fast. They can be fast, but they're not relativistically fast. So we've got non-relativistic motion going on, and it also makes it a lot easier to tap into then either basic descriptions of individual particles moving around, or if we're going to feed all of this into our statistical mechanics, which admittedly we won't be doing, but if you wanted to do classical thermodynamics with some statistical mechanics, just sort of tapping into it, then Newton's laws is certainly going to help with that. Then we need to talk about these particles hitting each other and hitting the walls of the container. So we're going to say that we've got collisions being elastic. So we've got no kinetic energy losses going on there, elastic. So this is saying that we've more or less got a contained system. We've got an isolated system with energy that's being conserved inside it. So we've got conserved energy because we don't have to worry about potential energy. We're not dealing with that at all. So yep. So we've got elastic collisions. We can also say that the collision time is negligible compared to the time between collisions. And this fits in with the idea that we've got these tiny particles where the size of these particles is negligible compared to the volume of the gas. This is tapping into assumption number 2 here, but the collision time is negligible compared to the time between collisions. So that's good. And it also feeds into I think this is going to be the last one that I'm going to be putting down here, that we've got that the forces, there's no forces between the particles except during collisions. So they're just moving around like crazy. And the only time you get these forces between the particles is during collisions. So the reason this taps into the previous one as well is that this is where you're going to get a little bit of potential energy here. If you've got these forces between the particles, then during the collisions, then you might have some potential energy kicking around. So we don't want to be including potential energy at all, not only internally, but just in general. We want to say the potential energy is zero. Okay, you can have little fluctuations for tiny amounts of time. We're saying these collision times are negligible. So these little occurrences of potential energy inside the ideal gas, they're just negligible because the collision times are negligible compared to everything else. So what we're getting at with all of this then is that we've got these particles with no structure. We're not considering any internal structure, that they are just moving around at random. So we've got a particular statistical distribution, and that there's no potential energy. So these are the three things that we're really wanting to take out of this. No potential energy, no internal structure, and whatever the other one was, I've now forgotten. Oh, the statistical distribution, and a Maxwell-Boltzmann distribution, which won't mean much to you at the moment, but it will do a little bit after a later video. So we're wanting to keep all of these things. So this is quite a long list of assumptions that we're making here, but it's not a bad set of assumptions. I mean, you can see the things that are going to make ideal gases fall apart. Yeah, if we're saying here we want no internal structure, so we're much better then. Ideal gases are going to work better with atomic gases rather than molecular gases. That's what we're going to want. As soon as you've got a molecular gas, we've got, I don't know, CO2, something like that, then we've got more internal structure. So we don't want that really. If we just got atomic gas, if we just got hydrogen flying around all over the place, then great. That's about as close as we can get to having no internal structure anyway, if we just got hydrogen atoms. So it's going to work better with atomic gas than molecular gas if we're looking at ideal gases. That's also going to fit with our, this comes with our potential energy as well, that both in terms of having this, internal structure being a problem for potential energy, but we're going to want to have low pressure. That's going to be much better for keeping all of these other assumptions, that we've got a size of the particle negligible compared to the volume of the gas. So if you've got a few particles in a massive volume, well, that really fits in with assumption 2. We're going to have a low pressure gas. You start increasing the pressure, you start putting more and more particles in. Well, 2 starts having a bit of a problem. We're also going to start affecting things with number 6, because you're going to be getting more collisions. You're going to have less time between collisions. So you're going to get a little bit of stress coming on there for 6. You might start affecting 7 as well, where you might start getting more forces between these particles. So you can see how this sort of stuff is going to start breaking down. So ideally, and that fits in with the ideal of an ideal gas, ideal gases, they work better for atomic gases at low pressure, because that's fitting in. I mean, high temperature as well is another one, which is quite a nice one to have. But, this works pretty well. So it's not like we're coming up with a ridiculously simplified description of an ideal gas. You can go out there and make actual observations of things that are happening in the universe, which are approximated very closely to ideal gas descriptions that we're going to have there. It's a bit like when we're dealing all that stuff we did in classical mechanics. Classical mechanics is brilliant in a lot of situations where you get very, very accurate descriptions and predictions from classical mechanics. There are just some cases when you've got relativistic speeds or quantum mechanical sizes and length scales and things like that, where classical mechanics falls down. But in a lot of cases it's great, and it's the same with ideal gases. It's very accurate in a lot of situations. There's just some situations where it doesn't work quite so well. So there you go. That's what we're doing with ideal gases. Those are the assumptions behind it, and it's always good practice, whatever part of science that you're looking at, is to know what your assumptions are. Know what the limits of those assumptions are. When do they break down? And it's as much a lesson in that when we're looking at ideal gases in actually constructing the description of the ideal gas, because this is the first time we've really had such a long list of assumptions. So you want to get used to that as a way of practicing science. Right, so there's going to be a lot more videos on ideal gases, because we can now go through, based on these assumptions, talking about, well, how can we actually describe these using mathematics? So we're going to have a whole load of properties and equations and things like that, both at a macroscopic and microscopic level, for describing ideal gases. So I'll do those over the next few videos.